The fixed charge problem is some of the applications of integer programming. There are other, applications of the integer linear programming, an employee scheduling problem. You have to learn this on yourself. I have that in the slides. The capital budgeting problem. Got to learn this also on yourself. I'm going to teach you the fixed charge problem. It's an important phenomenon. Now, guys, before we start, I want to share something with you. Something you probably already know. Because you are all doing economics, and so because you are doing economics, you will surely know of this. Now, in economics, there's something we have which is known as total cost. You all remember total cost. Total cost is given by fixed cost plus variable cost. You remember? Excellent. Now, if I want to draw fixed cost, so now what is fixed cost? Fixed cost is the cost that does not change with the level of production. Okay, so if you have a cost here, okay, and then you have a line. So let me just draw a line here. Okay. And then you have something else like this. Okay. And then you have a fixed cost, something like that. Okay. So this would be like a fixed cost. So this is your fixed cost. And this is your output there. Now that fixed cost can be a value of, say, 100. What does that mean? The fixed cost is that kind of a cost, in this case, which is 100, which doesn't change with the level of production. So the level of production was 10, went to 20, went to 50, went to 70. As the level of production is increasing from 0 upward, the fixed cost is not changing. Okay, the fixed cost is fixed. It's constant. Good. And so that is fixed cost. Now this fixed cost is what we are calling here fixed charge. Okay, so the fixed cost, and this is if you understand this basic principle, you are good to go. And I like it when sometimes I'm teaching and you say, I get it. You type I get it or something, then I know you are with me. So the fixed charge that we are going to look here is known as the fixed cost in economics. But of course, there is another cost in economics, which is what? The variable cost. Now, the variable cost, as the name sounds, is the cost that is changing or that is varies with the level of production. So the variable cost starts from, say, 0 here. Okay, it starts from, say, 0, and then it keeps going. Okay, so that's a cost that starts from 0, and then it keeps going. So what is that? Okay, variable cost. So as the level of production is going up, so it was here 10, then that cost is there. As the production increases to 50, the cost also jumps. As it increases to 70, the cost also jumps. So it is a cost that is changing with the level of production. And that is variable cost. So keep those two items in mind, because you are going to use that to address the principle of a fixed charge. Okay. Now, let's look at a storyline that will help us to better address this fixed charge situation. And I'm going to take a story that, is a practical story. Tema Textiles Limited. It's a company that produces clothes. Now, there are 3 types of clothing: shirts, shorts, pants. And this company engages in all of these. Now, the production of each type, and you've got to pay attention here. This is very important. If you lose slightly, you lose a lot. Okay. The manufacture of each type of clothing requires that the company has the suitable type of machinery available. Now, I want to repeat that. In other words, you can't produce any of the 3 types of clothing without having the machinery, suitable machinery, available in the first place. So which one depends on? So the clothing that you're going to produce will only be there if the machinery is there. So if the machinery for producing the product is not there, then this one too is what? Is not there. Now this is important because that gives us a principle of a binary there. something got to be there for something to happen. Binary. That's why I always say that binary is defined as simply as something that is there and something that is not there. Okay, let's move on. The machinery needed to produce each type of clothing must be rented. And if you go and buy the shirt machinery, the cost is 200 cedis per week. If you buy the shorts machinery, the cost is 150 cedis a week. Pants machinery is 100 cedis a week. Manufacturing also requires the amount of cloth. Now, that word is an important word because you're now talking about the amount of cloth and labor. Now, watch the word. It requires. So that means that these are like the resources that you need to be able to produce any or manufacture any of these clothing. And these are shown below. So let's look at them below first. So if you look at the resource requirement at the top here, right, you will notice that the clothing types, each clothing type will tell you the hours that are used to produce that clothing type. So you need 3 hours to produce shirts, 2 hours to produce shorts, 6 hours to produce pants. But you also need some cloth, square yards of cloth. So you need 4 square yards to produce shirts. You need 3 square yards of cloth to produce shorts, 4 square yards of cloth to produce pants. So you have all of these requirements. So keep it in mind, we are talking about some resource requirements here. Okay, and that is critical. Now, let's move on. We are told that each week, 150 hours of labor and 160 yards of cloth. And the word is available. That word available should always give you a clue that these will be on the right-hand side of the resource constraint. You see, the way I'm reading it to the extent of understanding it. And the same thing you do. When you are reading it, you got to read it with the intention of understanding it. You don't just read it, but you read to understand. Now, the variable unit cost, the selling price, okay, each type of clothing are also shown below. Now, that is important. Let's go down and see them below. So this is a revenue and the cost. Now, anytime we talk about revenue and cost, we are talking about profit, because profit is total revenue minus total cost. I'll come back to that. And in fact, let me just document that here quickly for you before we move on. Okay, this is an important phenomenon, so I want to just make that quickly. So total cost is usually, total revenue, actually, total profit. That's how we know it. Total profit. Okay. We normally refer it to as pi in economics. Total profit is total revenue minus total cost. Isn't it? That's how you know it. Total revenue minus total cost. And total revenue is price times quantity. Of course, total cost is also average cost times quantity. But I'll come back to that. So total cost is what? Price times quantity. And this is a price that are being shown here. So what you are seeing here are the prices. Sales price. Shirt is 12, short is 8, pant is 15. And then the cost. I told you the variable cost. Okay. So these are the variable costs. Okay. I wrote average cost. It's supposed to be variable cost. Okay. So these variable costs, more or less, is what you are seeing here. Now remember, the variable cost is the cost that is changing with production. So it means that this one will be multiplying the production element, which we shall come back to pretty soon. So keep that in mind, and then let's go to our situation that we are talking about. The question is this. We are not going to solve this, but rather formulate an integer programming problem whose solution will maximize weekly profit. Now, the essence of this is to just formulate it. I can give you this as a full-blown question. Just formulate it. And the formulation It's not as simple, and that's what we are going to just dissect right now. But the first thing we want to do in this formulation is to identify the decision variables. The decision variable, by going through the whole question again. So I'm going to just write here, let's identify the decision variable. Who has a clue of the decision variables that we are supposed to have? What is the clue there? The decision variables. Now, without even looking at it, you know the clue. But the question is how you identify the unit of measurement for it is important. Okay, the unit of measurement. So let x1 be equal to x2 be equal to, and then we can move on. Let me see. So, and Bertha says, yeah, rent and buy is good. It's an example of binary. Let x1 be the number of shirts manufactured. Okay. Now, why do you think, now that's good. X1 will be the number of shirts produced. Now, why are we identifying that to be number? Why are we identifying that to be number? Number of shirts produced. Okay. Now, this point of why are we identifying it to be number is an important thing to me. Okay. Number of shirts produced every week. Why? Why? Because the thing is that I told you earlier, let me just take you back to the storyline. Of course, before you do this, you have to refresh your mind with the storyline. So let's go to storyline. Because there's something in the storyline that will tell you that it's not a binary. It's not a binary. It's a pure integer. Okay. Or better still, it is we need a number of it. Okay. What tells you that we need a number of that? Well, the manufacture of each type of clothing requires that this is available. The machinery needed to produce each type of clothing must be rented and blah, blah, blah. Okay, now watch here. Watch in the next section. Machinery requires that the amount of cloth and labor shown each week, 150 hours of labor and blah, blah, blah available. Okay. And then the table, that's where the clue is. Selling price for each type of clothing. So if I tell you that the selling price for each type of clothing is 12, if I tell you that the selling price is 12, then I'm telling you that there is a certain number you can produce that will give you the total selling price for all the shirts. If I tell you that there is a selling price, there's a price attached to it, then it means that there is a number needed to make such production. So you have that selling price there. But you see, he doesn't even have to tell you the quantity available, because you should know that shirt will have a price. It means that therefore we need total price or total revenue. Okay. And this is how fixed charge is always done. Okay. You will need to understand it from that angle. So with that in mind, that is how come we got to know that there is a number. So this second one will be the number of shorts, okay, produced. Okay, the number of shorts produced. And then the last one, which is X3, will be the number of pants to produce. So these are your decision variables, but they are not your only decision variables. Watch the story. Who can tell me whether or not there is another decision variable? It's in the story. Okay? Because look at the sentence there. The machinery needed to produce each type of clothing must be rented. Now, the word decision variable is always something you're going to decide on. You're going to decide on the number of shirts to produce. You're going to decide on the number of pants to produce. Now, we are told that the machinery too must be rented. So we got to decide on the rentals. We've got to decide on the machinery for shirt. We've got to decide on the machinery for short. We've got to decide on the machinery for pants. So there's a machinery called pants machinery. We've got to decide whether we are going to rent it, or the word renting or buying is more or less the same. We've got to decide. But there's a clause there. There's a clause there. There's a clause there. Watch. It says that the machinery needed to produce. Now watch that word, needed to produce. So if I don't need a machinery to produce that particular clothing, I won't buy that machinery. So that machinery is only possible if I am going to what? Buy that particular, I'm sorry, if I'm going to produce that particular clothing. If I am not going to produce a particular clothing, I don't need that clothing's machinery. As an example, if I am not going to produce shirt, then I don't need shirt machinery to be in the warehouse. You see the word be there. So shirt machinery is only there if I'm going to produce what? Shirt. Pant machinery is only going to be there if I am going to produce pants. Now we can write that mathematically. We can write that mathematically. Okay. So I can say, let me just go up there and then show you something interesting. So I can say that XI, which is the clothing type, okay, XI, if XI, the clothing type, is positive, okay, if I'm going to produce it, okay, positive, then, oops, let me just clean this, okay. Then that particular machinery, let's call it YI, okay, that particular machinery is what? Is going to be there. That word there, sorry, did I say greater than? Okay. It shouldn't be greater than. It's going to be there. So what should I be? It shouldn't be greater than. It should be what? Okay. Somebody is thinking about what it's supposed to be. Yeah, this one, that's the correct answer. It's supposed to be equal to. Okay. So it's going to be equal to. So, and of course, let me call it YI. So XI is positive, is greater than 0. I'm going to produce XI provided I am incurring YI. So if I'm going to, so X1, which is shirt, the number of shirt to produce. If the number of shirt to produce is going to be positive, if I'm going to produce a certain number of shirt, then I must have incurred that cost of machinery for shirt. And so the machinery, the shirt machinery has to be there. And it being there means is 1. It not being there means is 0. And so on the basis of that, the next kind of decision variable, so I got to decide, okay, what I'm going to actually incur the cost of what? Of the machineries. So you can say that Y1 is equal to 1, okay, if shirts are produced, or 0, okay, if shirts are not produced. I can write this in English. Y1 is 1 if shirts are produced, or Y1 is 0 if shirts are not produced. The same thing I can say of Y2. I can say that Y2, okay, is binary, which is 1, if the X2 is being produced, or 0 otherwise. I can just say otherwise. Okay? And in this case, the otherwise will mean that, okay, they are not produced. And therefore, we can have Y1, Y2, Y3 as binary binary decision variables that are also there. I'll show you this very quickly in the note for you to appreciate it. Okay. So this is it. The cost of renting depends only on the type of clothes, not on the amount. So if I'm going to, you see, I just mentioned that if X is produced, okay, if any shirts are produced, any number of shirts are produced at all, I'm going to incur that. So you can buy that Y1, and the number of shirts you produce was just one. It doesn't matter, you have incurred it already. But you not only buy if you know very well you're not going to produce any shirt at all. So these become the other decision variables you have to add. So anytime you're doing a fixed charge analysis, you're expecting some binary decision variables like this. Of course, this will also go into the constraint as binary constraint. Okay, 0 or 1 constraint. This part is critical. There are two critical parts of what we're about to do. This is the first critical part, which I pray and I hope you understand. Now, so on the basis of that, we can say that our decision variables are 1. X1 is the number of shirts produced, X2 is the number of shirts produced, X3 is the number of shirts, and then we have the binary as well. We are done with our decision variables, but we are now left to write our objective function. Now, of course, the objective function is a bit loaded, but you're going to see it here. So the objective function. Now, objective function, by now, you should give you a clue that it is a kind of a profit maximization that we are doing. It's a profit maximization that we are doing right now. So we got to think of it like profit maximization. And I told you that profit maximization will represent it by pi. Okay, pi. And this pi is the total revenue minus the total cost. Okay. Now the total revenue, watch it. The total revenue is actually equal to the price times the quantity minus the total cost. And the total cost is the fixed cost plus the variable cost. Do you remember? Fixed cost plus the variable cost. So now let's try to get our sense of the total revenue in the storyline. What is the total revenue? Price. The price, was it given to us? Yes. The quantity is what we know as X1, X2, X3. So let's go to our preamble. Okay. And then look at it. Look at the revenue section. We have the price, the sales price here. So we're going to now, fit in this value for the prices. So we're going to have 12 of the X1. That's going to be the total revenue. Where the 12 will be the price, the X1 will be the quantity. Then 8 multiplied by X2. Then 15 multiplied by X3. This will form our total revenue. Okay. And most fixed charges are like this. Most fixed charges are going to be, tapping into this same principle, this same approach. Okay. So we need our total revenue well documented. And the first one is 12, 8, 15. So you now write your thing as 12, 8, 15. So 12x1 plus 8x2 plus 15x3. Okay. This becomes our total revenue here. And I want to believe that you all get it. You all get it. That is our total revenue. Now, what about our total cost? Now, remember, you have to bring minus, then the total cost. Now, the total cost involves a fixed cost. The fixed cost. And watch it carefully. The fixed cost was given. Take us back to the storyline. Watch it here. It says that the machinery needed to produce each type of clothing must be rented at the following rate. Now, why is this a fixed cost? Or a fixed charge? A fixed charge. Now, why is that so? Well, it says that it got to be rented. And rent is fixed. In this case, in this very same situation. So it says that, see, let me tell you, imagine you rent a shirt machinery, okay? You incur the cost of $200, 200 cedis, okay? You incur that cost. This is under the assumption that you are going to be able to produce. That's why you are incurring that cost. What if you do that and you just produce only one thing? And that one thing will not even reach any amount. So you have already incurred a cost. So this cost is fixed charge. It's a charge that is fixed. And so you can see that these are fixed. They are like the horizontal section of the cost curves. And so each of the Y's, remember these machineries are called Y's because they are either there or they are not there. Okay. So we are going to have 200 multiplying the existence of the machinery, which is our decision variable, our binary decision variable. So we're going to have this 200 Y1, okay, and then the 150 Y2, and then the 100 Y3, so that when you multiply, and then let me write it, then you can even appreciate why that is so. Okay, so you're going to have 200 Y1 plus 150 Y2 plus 100 Y3. Now, why? Now, you already know that the value for Y1 is either 0 or 1, isn't it? So if it is 0, then the whole of the 200 is what? Is gone. If all of them are 0, 0, 0, then there is no fixed cost. So remember, eventually, we know that the 200 is a fixed cost, is a cost, all right. But it is only going to be incurred, this 200 is only going to be incurred if Y1 is 1. The 150 will be incurred, is Y2. So the binary being multiplied by this doesn't really mean anything. Okay, they only mean 0 or 1. Okay, if the Y is 1 or 0. Okay, and so it becomes the fixed cost. And this is what must be captured in our fixed charge here. There's another part of the decision variable. Watch it here. It says variable cost. Variable cost. So this means that we got to now do minus, then we put into bracket the variable cost as well. What are the variable costs? Well, if you look at the storyline, you will know that there were some variable costs in there. Let's just go back and then you check it. This was given in the table up here. So you see variable costs was given there. Variable cost 648. And remember, they change with the level of production. They are not fixed. They change. That's why they are variable. And because of that, we are going to multiply them with the level of production, which is shirts, okay, the level of production, which is shorts, and the level of production, which is pants. We're going to multiply them by that. So 648, we add that into our analysis, and then we can now execute it. It is after all of this that we'll come back to the constraints. So we are still, on the baby stage. So now let's write our variable factors, 648. So you have 6x1, which is the shirt, 4x2, which is the short, and then 8x3, which is the pants. So on the basis of that, we can now put all together and write our profit function, or the Z max. Okay, now I can call it Z max or pi max. Okay, I can call it pi max, or now to go proper to linear program, I can say Z max is now equal to, okay, now watch it carefully, and I want you to be aware of this. If you look at this, the 12x1, it has some x1 here. If you multiply the minus by the things in the bracket for the variable cost, they are all going to be minus, 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 and they will now become like terms with the x1, x2, x3, the 12x1, 8x2, 15x3. So they are like terms, so I can subtract them easily, isn't it? So I can subtract the 12x1 minus the 6s1, the 8x2 minus the 4a2, okay, and then the 15x3 minus the 8x3, because they are like terms. I can't do the same thing for the y. I can't do the same thing for the y because they are not like terms. So on the basis of that, 12 minus 6 will give you 6. So this gives us 6x1, okay, plus 8 minus 4 will give you 4. So you get 4x2 plus 15 minus 8 will give you 7. So you get 7x3. Okay. Then minus the y's. They are not like terms. And now I'm expanding the minuses. So it will be minus 200y minus 200y1 minus 150y2 minus 100y3. Finally, this is our Z max. This is our objective function. Ladies and gentlemen, right now, as you look at objective function, it might look very, very confusing like Hebrew. But hey, we know where we are coming from. We brought it to this level. We worked it out ourselves. We went through it step by step, and we got our z-value. It might look like a little bit strange z-value because we've never had a z-value where you have two kinds of decision variables in there. But hey, you are going to see that this is easy. This is easy. Easy peasy. So now that we got a decision variable, we'll now go to the constraints. What are constraints? Well, if you go to the storyline, the constraint was obvious in the story. It says there, up there. Each week, 150 hours of labor, so labor constraint. 160 hours of plot, so plot constraint. So we're going to have the right-hand side, 150 and 160 for the labor and cloth. Those are the first ones. So I'll just put that one there. And they are available, so it's just going to be less than or equal to. Okay, this one is a guaranteed less than or equal to. Somebody is asking, where was the 7x3? Now the 7x3 was the 12, okay, 15. Watch it. This 15x3, okay, it has a light term, which is the 8x3. So 15 minus 8 is 7x3. 15x3 minus 8x3, 7x3. We're just doing light terms, okay? All right. So on the basis of this, we can now move ahead and then write our constraints. So constraints, first constraint is a labor constraint. And like we just indicated, the labor constraint is 150 hours. And then the cloth. So we just put there 150 hours and then the other one 160 cloth. So what is going to be on the left hand side for the labor? Well, go to the story here. Go to the story here, and that will tell you the beautiful thing. Now the story says, and you can normally get this. Okay, look at it. They are right there under the resource requirement. Labor is 326, and then the cloth is 434. And each one of them will have the short spans. So x1, x2, x3. So 326, we document that. Okay. So you are going to get 3, 2, 6. And then the other one is 4, 3, 4. Okay. And this is for the x1, x2, okay, and then x3. And then this is for the x1, x2 plus, and then x3. So these are your constraints. As easy as they may sound, this is it. Okay. Then, of course, you have to determine now your non-negative. There was no other restrictive constraint, mixed constraint anyway. Okay. So now we have to write our decision variables. Okay. Then integrality constraint, the non-negativity constraint, in this case, the binary constraint. Now, first thing we know is this, that the x1, comma, the x2, comma, the x3 are greater or equal to 0. This is a non-negativity constraint. And then and integer. And integer. Now why and integer? Because we are expecting the shorts, pants, and then the shirt. We want these things to be whole numbers. Because we can't have decimals shorts, decimals pants, and all of that. Okay. So one full one. And then we get number of that. So this is it. Then we also had a y. 1. Okay, we had a y1. These are things that we all know already. y1, y2, y3. And this is also supposed to be equal to 0 or 1. I need to make that clear. Okay, equal to 0 or 1. Then you add binary. 0 or 1 binary. Okay. And so our presupposed final solution is going to be this objective function. Okay. See, the beauty of this is your ability to be able to capture what is here. So this is our objective function here, each one of them. And then we have what? We have our constraint. Now, if you check carefully, and I want to make this point clear, if you check carefully, these constraints, where's that? If you check carefully the constraints, okay, you will see that, sorry, the objective function, you will see that we have the y's as well in it. So this becomes that then subject to will be the next thing to deal with. Okay, subject to, and then finally you will have your ones here. Okay, you will have your beautiful constraint there. Any question on this before we move on? Because I have a question for you. If you don't get a question, I have a question for you. It's a very deep question. Okay, so let me show you this in the answer section. All of these have been done, but let me show you something interesting. By the way, when you check your notes, you see that all of these are there. I have a question for you. So this is a final formulation. This is a final formulation. And the last two are the integrity constraints. Is this whole formulation correct? Is it correct? Yes or no, and why? Is this correct? Of course, this is wrong. What we just did is not correct. Now, it's not correct doesn't mean that this is not correct, but it's not correct in the sense that there's more that is needed here. Why? First thing, if we solve this optimal solution, this is what we are going to have. X1 will be 30, X3 will be 10, X2, Y1, Y2, Y3 will be 0. What is the problem with this solution? Who can raise a hand and tell me? Look at the solution very carefully. If we get this solution, what is the problem? Based on your understanding up to where we are now, what is the problem with this solution? There's an obvious problem right there. Obvious, clear. Remember our understanding of the machinery and all of that. There is an obvious problem right there. Okay, Kelly seems to have a way to address that problem. Yeah, Kelly.
So if I understand correctly, if you look at Y1, Y2, Y3, it shows that we're not supposed to produce anything.
Sorry, you were speaking.
Things Y1.
Take your time.
Oh, sorry. Things Y1, Y2, Y3, which is it determines if we have to produce or not, is 0. It indicates that we are not supposed to produce anything. So X1, X3 was not supposed to be available.
Good.
Because the machines were not available.
Yeah, perfect answer. Excellent. It just shows that you are learning. You are not sleeping at all. You see, what this means is that if you are telling me that Y1, Y2, Y3 are 0, if they are 0, if the machinery were not bought, if the machinery cost us 0, then their X's must also be 0. Because you can't produce X1 shirts without incurring a machinery cost for shirts. That's the point. That's the simple answer. Okay, and that's exactly what she has just executed. Okay, and this is it. You can't produce X1 and X2 with a 0 rental cost. So we got the simple reason is that we did not account for the Y's in the constraint. So if you look at the formulation, the Y's have been accounted for right here in the objective function. But in the constraint, inside these constraint section, okay, from these constraints, okay, we did not have the Y's accounted for. And I'm not talking about the binary section of the Y, no. We didn't really have Y's accounted for at all. So there's a problem. So you've got to account for it. And to do that is the main essence of fixed charge analysis. That's the main essence. This is going to be fast. This is going to be fast because of the time. Okay, so let's enjoy the next process. The next thing is this. We're going to make an assumption of how to capture. We call it a linking constraint. We're going to create something we call a linking constraint. What is a linking constraint? A linking constraint is a constraint that links the X and the Y's together because there's a relationship there. And the relationship is linked like this. Every Xi must be less or equal to Mi and then Yi. This is a linking constraint. Every Xi must be linked with Mi and then Yi. And so it means that we must have X1 less or equal to M1, Y1. And then X2 less or equal to M1 and then Y2. 2. Oh, M2, Y2. Then X3 less or equal to M3 and then Y3. These must be linking constraint. But of course, the first thing you're going to ask is that what is this M? What is this M? Now, in order to understand the M, you've got to be slightly confused. It's a trick we are using. You've got to be slightly. M is the upper bound for the X. M is the upper bound for the X. M is the upper bound for the X. So M is actually one of the X variables, but the highest value for the X. M is one of the X values, but then it is the highest value that X can take. Now let me give you an example. Let's say that we are producing, we are incurring machinery costs, so Y1 is 1. If we are incurring Y1 to be 1, if we are incurring Y1 to be 1, if you multiply that 1 by the M1, that gives you what? M1. So it means that the whole of the right hand side will be what? M1. Yeah? This whole of this will be M1 if Y1 is there, if Y1 has been incurred. So it means that X1, listen carefully, X1 is less than or equal to M1. Do you agree with that? It will mean that X1 is less than or equal to M1. Ah, that's good. If it is equal to M1, then if you forget about all the less than and you use the equal to, it means that the highest value that X1 can have is the M1. Ah. The highest value that X1 can have is M1. The others are all going to be the less than part. The less than part. That is why we say that the M1 or the M's are the upper bound for the X's. So how do you get an M? How do you get an M? Because we need M. It has to be a number. We got to know it now. Well, it's a very simple thing. Watch it. Watch it. Watch it. Now, in order to get M1, this is what you're going to do. Okay? In order to get M1, and I'm going to write this here. To get M1, okay, assume that X2 and then X3 are 0. Now, because I'm going to get M1, it means that I'm going to get X1, its highest value, isn't it? It means I'm going to get X1, its highest value. So I will not equate the X1 to 0. Okay? I will rather equate the X2 and the X3 to be 0 in each constraint. In each constraint. Because this is a linking constraint, in each constraint. Okay. So we need to get the two constraints, and wherever we see the two constraints, and wherever we see X2 and X3 in each of the constraints, we are going to equate them towards 0. And then we will find the value for the X1 there. We'll find the value for the X1 there. But before that, let's remind ourselves of the constraint. The constraints are 3x1 plus 2x2 plus 6x3. We are going to use equal to because we want the highest values. Remember, anytime we are using, we want the upper limit, the boundaries, we use the equality part. Okay, not the less than part. The less than part is usually the space. Okay, so 3, 2, 6. We are going to write that. See? So for constraint 1, we have the 3x1 plus 2x2 plus 6x3 equal to 150. Okay, that is for the constraint 1. That's for the constraint 1. Now for the constraint 2, in case you remember, and of course you do remember, the constraint 2 is 4, 3, 4. Okay. So we are going to have 4x1 plus 3x2 plus 4x3 equal to the upper bound was the equal to sign was 160. So this is what we are going to do. What we are going to do now is that wherever we find x2 and x3, we are going to have it as what? 0. Okay. So watch. Okay. Watch it here. At this time, we are going to now and calculate the value of x1. So wherever we see x2 here, we'll put 0 there. Wherever we see x3 here, we'll put 0 there. So that means that to get x1, If these things are 0, then we are going to have 3x1 equal to 150. Do you all agree? Do you all agree? Excellent. And so that means that x1 is what? That means x1 is what? 150 divided by 3. 15 by 3 is what? It's 5, 0. So now you're going to get what? A value of 50. A value of 50 when x2 and x3 are 0. But that is for the one constraint. That was for one constraint. So you have to do it for the other constraint. Because the constraint in this case are 2. The constraints are 2. So you have to do for the 2 constraints. Every one of, if the constraints were 10, you do it for each of them and find each of the x's there. So let's go to the second constraint. If x2 is 0 there, and if x3 is also 0, okay, if these x's were 0, the question now is that what will be the value of x1? So it means that you will now be left with 4x1 equal to 160, which means that x1 is 40. So in this situation, in the first constraint, x1 is 50. In the second constraint, x1 is 40. Which one do you take? You take the smaller x. Always, you take the smaller x. I'll teach you. In fact, you come out with yourself, okay? You come out and you come to realize why that is so yourself. We take the smaller x, okay? And so that smaller x now becomes what? The m1. So in this case, our m1 is equal to 40. Now we go to m2. Now m2, okay, so to get m2, this time you have to assume that x1 and x3, not x2, x3 is also 0, and find the value of the x2. So you go to the same constraint here. This time, wherever you see x1 and x3, they are going to be 0. So look at the first constraint. x1 is going to be 0, x3 is going to be 0, so you are going to be left with 2x2. So you'll be left with what? 2x2 equal to 150, which means that x2 is equal to 75. Okay, that is it for the constraint 1. Now, what about the constraint 2? Constraint 2, you'll see that x1 will be 0, x3 will also be 0, so we'll be left with 3x2 equals to 160. So you write 3x2 equal to 160, which means that x2 is equal to 160 divided by 3, that is 53.33. Is that correct? 53.33, I guess. Yes. 53.33. Yes. So we can round it and say 53. But at this stage, you're going to select which one of them. Okay? Are you going to take the 75 or you're going to take the 53? Which one? Obviously, it's going to be 53. You take the smaller one. So we can now say that our M1, finally our M2, our M2 is now 53. Let's just round it here. It's 53. We are left with the M3. Now watch me, this is the last one, M3. So to get M3, but let me use a different writing so that it would look good. Okay. To get M3, we are going to assume that x1, x2 is 0. So wherever we see it in the constraint, we find the value of x3. So that means that these parts here are all going to be 0. Okay, these parts here are all going to be 0. So we'll be left with what? The first constraint, we will have 6x3 equal to 150, which means that x3 is equal to 150 divided by 6. What is the value of 150 divided by 6? Okay. I think it's going to be decimal. It's 25. Yeah, 25. 150 divided by 3 is 25. Yeah. 25. Okay, 25. And then you have, let me be sure. And then you have the next one to be 4x3 equal to 160. So x3 is equal to 40. So again, we have 25 for one. Okay, we have 25 for one, and then we have 40 for the other. So our M3 will be the smaller one, which is 25. So finally, we can write all of our constraints now. Okay. I'm going to rewrite that linking constraint that we dealt with. Remember, the linking constraint was xi equal to mi yi. Sorry, less or equal to mi yi. So the first one will be x1 less or equal to, then remember that constraint, which was what? 40. So it will be 40 y1. Then the second one was x2 less than or equal to something y2. But that value, let's get it here, the smaller ones. Okay, we have 53. So this is going to be 53 y2. Then the third one was x3 less or equal to 25. That one I remember it easily, 25y3. So now we have this constraint, but I can move them to the right hand side. I can move this. Let me just show you, because you know what I'm just doing already. I can move this section here to the left hand side so that I'll be left to 0. Okay, so then it becomes minus. Okay, I can just do that. 53.3, but I've just rounded it up to 53, so don't worry. Okay, you can keep it in decimals. So eventually what is going to happen is that I'm going to be able to have this as x1 minus 40y1 less or equal to 0. Okay, x2 minus 53.33y2 less or equal to 0. I'm just moving them. x3 minus 25y3 less or equal to 0. So we are now going to add this one to the constraint, and then that'll be it. Finished. Okay. As for all others, we know them already. Okay. Watch the slides, you'll see all of it in the slide. This is our final constraint. The maximized constraint, you know it. The subject to constraint. Now we've just brought in these. We brought in these particular values. Okay. These particular values that we have, they make the big deal. Somebody says they are the big deal. Okay. For me, they are the ones you should love. This one, okay. These ones, okay. These ones are the ones you should have love for. Okay. They are the ones that you should have love. So everything that is here, that's what matters. Everything. This is where your love must be. And this one, we can change them. We can change them and move to the next section. Okay. We can change them. And one way you can change them is, let me just go back here. You can see that I have actually moved them to the left hand side. And so eventually, those become our constraints. This is the fixture. Once you've been able to do it like this, you are done. You are sorted. Now suppose we now go and work this in the Excel. It will not give us strange answers, and I did it. You can later formulate this in Excel and see. And when you do that formulation in Excel, this is what's going to happen. You're going to have these values. The optimal solution is going to be Z will be 75, X3 will be 25, Y3 will be 1. And you can see that now that we are producing pants, there's no problem if we incur the cost of pants. So Y3 now has to be 1. And this becomes the final solution. So if we make any shirt at all, no matter how many we make, we must pay for the fixed charge of 200 to rent a shirt machine. Okay, we must do that. Okay, even if we do that, but this, in this case, pants, we need to do that for pants rather than to do for shirts. So this is how we formulated it in Excel, and you can try it on your own and formulate them in Excel, and it will look brutal for you. This is the Excel formulation. So ladies and gentlemen, that is how you do the fixed charge. Fixed charge, the principle uses economic principle, and you will always be able to execute this in a beautiful, beautiful fashion. That brings us to the end of fixed charge.